All right, so let's see. Let's start with this boundary condition here. That's the easier one. So if I transform this boundary domain condition from the time domain to the S domain, it's pretty easy, right? On this side I have t hat as x goes to 0, and on this side I have a constant. The Laplace transform of a constant is that constant divided by s. So here's my boundary condition in the S domain. I have to make this solution here satisfy this boundary condition. So I plug in x equals infinity here and here, which I have here and here, and I set it equal to t initial divided by s. So this exponential of infinity is infinity, exponential of minus infinity is 0. So this equation says that c1 times infinity has to equal 0, and the only way I'm going to make that happen is if c1 is equal to 0. So one of my boundary conditions, because I chose exponentials, made one of these two terms go away. This term goes away, and I'm left only with this term associated with C2. So that was progress. The next thing I got to do is take this boundary condition at x equals 0 and transform it to the S domain. So let's see, I can do this term by term. This is a constant, so that gives me the constant over S. This is a linear term, and if I go look in that table, I'll see that this linear term becomes beta over S squared. So this is t, this becomes t hat at x equals 0. And then I have minus k, and this is a derivative with respect to x. Derivatives with respect to x remain unchanged, so this is dt hat dx at x equals 0. So this is my second boundary condition, and I have to make this solution agree with this or perform like this at x equals 0. So all I do then is I plug in x equals 0 here and substitute it into this boundary condition. So let's see, I have this term, I have this term, and then this is this thing evaluated at x equals 0. So on the other side I have minus k times the derivative of this evaluated at x equals 0. So that gives me this right here. So let's see, this cancels with this. This is 1 and this is 1. Exponential of 0 is 1. So I have this equation here, which is my second equation. This is an algebraic equation for C2. So if I solve for C2, I get this. I plug that back up into here, and here's my solution, right? This is no longer a general solution. This is the specific solution for this problem. This solution obeys both of these two boundary conditions, right? So I have now solved my problem in the S domain. As promised, it was easier, right? Because it was an it was an ODE in the S domain rather than a PDE in the time domain. The last thing I got to do is transform this S domain solution back to the time domain, right? And that actually ends up being tricky. If I look at, let's see, if I look at this equation here and I go to my table, I don't find anything that really looks like it. There's a few things down here that look kind of like it, but nothing that actually is like it. You know, I can try to get bigger tables, and maybe in some book somewhere I might find it, but that seems like it's not going to work. I could go to Maple and say, well, Maple's got the power of 10,000 mathematicians behind it. They tell you that every time you open the software, so let's see if that works. So I plugged this equation into Maple. This is this right here, and then I said, well, inverse Laplace transform this from the S domain to the time domain, and you can see what Maple did is just take this and throw the IMV Laplace indicator in front of it, which is basically Maple's way of saying I can't do that, right? So that didn't work either. So I'm kind of stuck with this third option right here, which is let's use one of these numerical inverse Laplace transform functions. So that's what I did then. I went to MATLAB and I wrote a function. I called it Laplace2 that implemented my solution in the S domain, right? So again, just to remind you, it has to take in a vector of S values as well as whatever other parameters you need to implement the solution, but a vector of S values and return a vector of t hat values, right? So I'm expecting this function to get a vector of x values, but s values, but then you also have to give it, you know, if you look at this, x and alpha and t initial and k and h bar and beta, right? So that's what all these extra guys are. And then I didn't use a loop this time. I used the dot indicator, which or the dot operator, which means I'm gonna do the same operation to every element in a vector, right? So whichever you're more comfortable with, it doesn't really matter. But this is actually a vector of t hat values, and I can test to make sure that works. Once I'm convinced that works, then it's just a matter of using any of these numerical inverse Laplace transform functions. I used Talbot inversion, which I posted on the website, and I didn't monkey with the number of terms in the series. There's an extra third argument you can use if you want to, that will change the number of basically the numerical parameters it uses. I don't know enough about it to do that very intelligently, so I left that alone. But I did send it the two arguments that it needs, right? So I took the function that I wrote here, and I mapped it to being a function of s. So that's the function that it's using, and then I'm giving it a vector of times, and my vector of times goes from it goes 24 seconds. And I will point out that when you use any of these things at very short times, it tends to not work very well. So there's some time below which it's not going to work very well. And I did this initially at 1 centimeter deep into the material, and I did the same thing again 2 centimeters deep and 5 centimeters deep and 10 centimeters deep, and then at the surface itself. And I made a plot of all these different positions as a function of time. So if I run this somewhere, I should see a plot. I guess it's right here. And this plot is showing the temperature as a function of time. Right? I should have labeled that, but this is the surface temperature, and this is a little deeper and a little deeper and a little deeper. And of course you can see that the surface temperature responds basically instantaneously, whereas these temperatures farther in take a little time. So there's a little bit of time here before the temperature 1 centimeter deep knows anything happened. And then there's a longer period of time before the temperature 2 centimeters deep knows anything happened. So you can sort of see that. If you prepare a plot, somewhere I did this here, showing the surface temperature as a function of, that's not what I wanted to do. Where's my, okay, as a function of time. So this is the temperature at the surface minus the initial temperature. This is the surface temperature rise as a function of time. You can actually see, if you go over several orders of magnitude of time, you can see this initial proportional small time period, and then you can see that the slope kind of flattens out, and you go to this long time period. So initially 1 decade here is going to give you 1.5 decades of temperature rise, which is what we thought would happen. And then eventually 1 decade here gives you 1 decade of temperature rise, which is kind of what we thought would happen, right? And if you calculate the characteristic time for the inputs that I put in, it's around 2 seconds. And sure enough, if you're much less than 2 seconds, you're in the short time regime. If you're much greater than 2 seconds, you're in the long time regime. So there's this region here where you're transitioning from one to another. Okay, so that is Laplace transforms. Obviously there'll be a homework problem that utilizes Laplace transforms, and at this point then you have two kind of tools that you can use to attack transient problems, 1D transient problems numerically, right? One being separation of variables, which is typically used for bounded type problems, and then the other being Laplace transforms, which you'll find are useful more often for semi-infinite body type problems, right? Both are pretty useful. Both are really handy. What we're going to do next is actually do numerical solutions to these kind of problems, right? And that's kind of an interesting mashup of the numerical solutions to 1D steady state problems, which we talked about a long time ago, and then numerical solutions to lumped capacitance problems, where you're integrating a state equation through time. So we're going to sort of smush those together, and what we're going to end up getting is not one state equation, but a whole set of state equations, one for every node, and we'll have to integrate all those state equations through time using basically any of the techniques that we talked about before. And those numerical models are really flexible and really pretty powerful. One of the reasons that you would like to have these analytical approaches is actually so that when you're dealing with the numerical model, you have some place to go to verify that it's working right. So that's one of the main reasons that you'll see people use analytical models, is just as a verification of a numerical model to make sure they can trust it. And then once you have the numerical model running and you trust it, it's so much more flexible than these analytical models that a lot of times you do what you need to do with the numerical model. All right.